motion of the planets around the sun is a lecture to be looked forward to every year for a couple of reasons. One is that very often when we're talking about universal gravitation, we encounter these observations made by Kepler, particularly, that the motion of the planets around the sun are not in fact circular, but are ellipses with the sun at one focus. And Isaac Newton provides us the explanation for that motion in the form of universal gravitation. And so what you typically do as a teacher of physics is you say, well, it's a remarkable thing, and Newton was very clever. And he was able to prove, based on a 1/r squared force law, that the resulting motion would be, in fact, elliptical. And then you move on to applying universal gravitation. You never actually solve it. And so it should, hopefully it happens from time to time in the mind of the student. The student thinks, well, no, let me see that. Let me see that demonstration and see that it's true. So you might imagine that today I could come in here and show you exactly what Isaac Newton's demonstration would be for the motion of the planets around the sun. In fact, I won't do that, and it's entirely possible can't do that. Because in order to solve the problem, Isaac Newton had essentially invented the method of calculus. And also, in his time, Newton was accustomed to making very geometric arguments for the solution of problems. And so if we were to sit down and study as a historical matter the demonstration that Isaac Newton would have done, we would find it quite complicated indeed. Could perhaps make months and months of study trying to figure out what it was that Isaac Newton was talking about. So what I'm going to do instead is give you a formulation, a demonstration of sort of my own design that will be very, very different from Newton's approach. I think at some point I'll probably say specifically what the major difference is between what I'm doing. But that doesn't mean that my approach is illegitimate. It's just more sophisticated and done from a sort of a modern point of view, understanding our physics perhaps a little bit more deeply than even Isaac Newton did. So that's what I'm going to be doing. Along the way, one of the good things about this demonstration is we can help you, the student, to appreciate how truly skilled you are to follow the arguments. Very often when we're studying physics, we feel a little bit beaten up and kicked around by the problems that we're asked to solve. And it's difficult for us to appreciate that, in fact, in a short time, we've come a long way. So please, this is partially for your entertainment and also for your edification. Just try to follow the arguments. Also, what I'm about to do is sort of off the top of my head and algebraically a bit sophisticated. So if you see me make a mistake, which I hope that I do not do, but if you see me make an algebraic mistake or I do something that concerns you, please point it out. So what I'm going to be doing here in the space that I have available to me is demonstrating that if I make the assumption that the force that is the cause of the alteration of the motion of a planet in orbit is a 1/r squared force, make the assumption that if that is its nature, then the shape of the resulting orbits will in fact be elliptical. It's a theoretical demonstration that is verified by astronomical observations of the motion of the planets. You see, I learned that I have the force law right if I use the force law and see what would the shape of those orbits be, and I find out indeed that they're ellipses. But in order to do that, the very first thing that I have to do is make sure that when I get to the end, when I get to the aha moment, we all know what I'm talking about. That is, we know what an ellipse is. It's a matter of elementary mathematics to describe ellipses, but I just have a little summary that I want to give for the ellipses here so that we all know that we're talking about what we're talking about. It's entirely mathematical here. That I know that an ellipse is sort of like an oval. It's not actually an oval, according to its mathematical definition, but there's a way that you can say it in words that's quite difficult, that an ellipse is the locus of all points, the sum of whose distances from two foci is a constant, which is sort of an elaborate way in words to say that. But here I've drawn the ellipse, and I can write a mathematical equation that expresses the ellipse in Cartesian coordinates. It looks a bit familiar, perhaps. If you remember enough from your elementary mathematical education, you recognize it and say, yes, I see that x squared over a squared plus y squared over b squared is equal to 1 is the traditional Cartesian coordinate representation of the ellipse. Now here on my ellipse, I've labeled what a and b are. Here a is drawn from the center of the ellipse, which of course is immediately between the two foci, from the center of the ellipse to the furthest extent of the ellipse. That is, this is the largest axis of the ellipse, and so therefore is called the semi-major axis, just labeled down here so we know the nomenclature. And then I have another axis drawn from the center to the narrowest extent of the ellipse, which is traditionally called B, the semi-minor axis. And A and B, of course, are not equal to each other, which is what essentially creates the shape. Because imagine, for a moment, if I selected A and B to be equal to each other, then here in my equation, in Cartesian coordinates for the ellipse, a squared and b squared would be the same number, which I could factor out and multiply to the other side, and then I would have x squared plus y squared equals, let's say, r squared, the equation of a circle. You see, you've heard me from time to time say that a circle is a special case of the ellipse. It's the case of the ellipse when the semi-major and semi-minor axes of the ellipse are in fact equal to each other. So it would be a remarkable demonstration if I could do a little bit of physics here and make some rational, logical arguments, and then get to the end and say, hey, look, x squared over a squared plus y squared over b squared is equal to 1. It's an ellipse, and that would be my aha moment. But it turns out, spectacularly, that Cartesian coordinates is not the favorable set of coordinates in order to solve this problem. Remember always in physics that the choice of coordinates is mine. It's up to me. I can use whatever coordinates that I like. And now we've realized through problem solving that some coordinate systems are better than others for the solution of problems. So perhaps there's a coordinate system that is more convenient. Indeed, it's true. I'll add to my ellipse here a planet that happens to be moving along that ellipse, which I'm not assuming that that's true. I'm going to demonstrate, in fact, that it's true. But here's the planet on the ellipse, and naturally it moves with a velocity v that is tangent to the ellipse at every point in the direction of motion. In principle, if it's a planet going around an elliptical orbit. So I can define that position by x and y coordinates. Absolutely, it's true. But I can also equally describe it in what you would term polar coordinate, with a radius vector that points from one focus to the planet. That, in fact, is the focus where I'm going to say my star is. The star that is creating the gravity that is causing the alteration of motion of the planet. So there's the star, and the location of the planet is described by a radius r, and that radius vector changes the entire time, all the way around. And an angle theta that I've chosen to measure arbitrarily from this axis. The fact that that angle is measured arbitrarily is going to actually come into my derivation a little bit along the way. I'm going to take advantage of how I choose where the zero angle is measured from. But at any rate, there's the angle and there's the radius, and so I can write the equation of an ellipse in polar form. No matter what your elementary mathematical education, it's probably true that you've never seen an ellipse written in polar form before, but it's easy enough for you to derive it, and you might want to do it as a little side activity if you find yourself with a piece of paper and a pen and some downtime, kind of a desert island situation. But if I realize that the x position according to the center of the ellipse would in fact be, here I've drawn that I've labeled that the distance between the two foci is 2c, where c is what's known as the focal distance of the ellipse. That the x-coordinate of the planet at any point in time is going to be the focal distance plus r cosine theta, and that the y component, or the y position of the planet at any time, is going to be equal to r sine theta. I can make those substitutions in the equation of the ellipse, and after some algebraic machinations and battles and wrestling, I can demonstrate that the equation for an ellipse in polar form is this rather oddball looking thing here. Notice that what I have is the radius as a function of angle. So you tell me an angle, I'll tell you what the radius is, and that completely describes the ellipse as adequately as x and y does. So here I have some constants involved. There's A, the semi-major axis that appears, and this curious creature E, which is called the eccentricity of an orbit. The eccentricity of an orbit describes how sort of stretched out it is. Consider again, if A and B are equal to each other, the way I have the eccentricity described here is the square root of 1 minus b squared over a squared. If B and A are equal to each other, then this is 1 minus 1 is 0, and the eccentricity is 0, the orbit is circular. The eccentricity is 0, and the orbit is circular. Notice that B is always lesser than A, according to the way they're defined here. So this ratio is always a number less than 1, which is nice because it means that the inside of this radical remains positive, and will be the square root of a number less than 1, which will be a number less than 1, until B becomes 0, and this becomes the square root of 1, which is 1. So an orbit with an eccentricity of 1 is a line, and an orbit with an eccentricity of 0 is a circle. The eccentricity describes the ellipticalness. Right? It's a very traditional mathematical quantity to draw in there. So the eccentricity appears, and so there are two parts to this thing. First of all, the angle theta, which describes the position, has a name. The only reason I've listed the name here is because I think it's a really cool sounding name. That's my sole purpose for pointing it out. The angle in this form is called the true anomaly. I don't know. It's just called the true anomaly, and that sounds really special, so I thought I'd mention it. And the numerator of this polar form is referred to as the semilatus rectum of the orbit. It turns out that I can describe that here on my diagram. It is from the star here, or the sun, at this one focus, the perpendicular distance, that is perpendicular to the major axis of the ellipse, to the ellipse, like that. It's called semi because the entire distance from one side of the ellipse to the other would be called the latus rectum. The semilatus rectum is just that one part. So I'm going to give that a name and call it capital L, which is sort of traditional. And so here I have my ellipse written in polar form. And I put a box around it because that's where I want to end up. So the whole purpose of this discussion is to educate you as to what my aha moment is going to be. I should, if I'm careful, diligent, apply my physics very carefully, that is the result that I should get. When I make the assumption that the force that is the cause of alteration of motion is Newton's universal gravitational force, and I've already given the reasoning why it should be thus. By action-reaction, it should be the product of the masses, and according to the intensity distributed over the surface area of a sphere, it should be 1 over the square of the distance. That's what I imagine that it is. The question is, does such a force result in elliptical orbits? Now, what Isaac Newton would do in his demonstration, however that works out, is he would start with the force and say that the force is the cause of the acceleration. Newton's approach would be F equals ma. And he would write that as a differential equation that he would somehow find a way to solve, like we have done in the past. Like, for example, with viscous drag. We write Newton's second law. We find a relationship among the rates of change of the quantities. We integrate, there comes the calculus in it. We integrate those equations to find the velocity as a function of time. Newton would have done a similar thing. It would have looked very, very complicated. I am going to take a different approach. I'm going to take a different approach according to the philosophy of our physics, that virtually all problems of mechanics are best solved from the point of view of energy. So I'm going to start my approach with an expression of the total mechanical energy of a planet in orbit around the star. So the total mechanical energy, which naturally I call E, is going to be a sum of two contributions. The kinetic energy, 1/2 the mass multiplied by the speed squared, minus, recalling that the gravitational potential energy is always negative for bound orbits, G mm divided by r. Now you might immediately think that I've gotten off track here, because you say our goal is to demonstrate that it is the 1 over r squared force that is the cause of the motion, and if you do this energy approach and you have the kinetic energy and the potential energy, the force will not appear in the argument at all. Well, in fact it does, because how do I derive the gravitational potential energy? I integrate the force, computing the work done by the force, which is equal to the negative of the change of the potential energy. So the force is in this expression in that I needed the 1 over r squared force to get gmm over r. That is, the universal gravitation is built in to the gravitational potential energy. So this is how I'll proceed. I like the fact that my potential energy is in terms of r, because r is one of the coordinates that I use to describe. So I like gmm over r very much, but 1/2 mv squared is a quantity in this demonstration that's going to give me a little bit of trouble, because the velocity vectors I've shown here in my diagram is off at some, not arbitrary, but some angle according to its position on the ellipse. And so it has components, x and y components to the velocity. Well, x and y components of the velocity is a Cartesian sort of idea. I'm not interested in that. I'm interested in the velocity in its polar form. So the very first thing that I'm going to do is take that kinetic energy there and create the polar form of it, which is an exercise that happens in solving quite a few classical problems of mechanics. But here I go. The velocity squared I'll focus on. Isn't the velocity squared, in fact, the x component of the velocity squared plus the y component? Well, that's not. Plus the y component of the velocity squared, vy squared. That's true. But there's a notation of convenience that we like to use here that I've mentioned to you before, that very often physicists will express the time rate of change of a quantity with a dot. That is, the x component of the velocity, which I've written as vx, is actually x dot squared, where the dot denotes a time derivative, plus y dot squared naturally is the y component of the velocity. So my initial question was, what is the velocity squared? And now I recognize that it's the sum of squares of these two components, vx and vy. But I have to convert those components into the polar form. So what I'm going to realize, looking carefully at my diagram, that x in this coordinate system, now bear in mind the coordinate system here is shifted. It's not the center of the ellipse, but is in fact the sun as one of the foci. That the x component of the position is in fact r times the cosine of theta. According to my diagram there, it's equal to r times the cosine of theta. And so what I need to compute here is what is r dot, x dot, the time rate of change of that position. So x dot is what I'd like to do. So I have to take the derivative of x is equal to r cosine theta. Be careful. I'm taking the derivative of x with respect to time. And r is a function of time. Imagine the planet going around in orbit. R changes as a function of time. It gets longer and shorter through the course of the orbit. And theta, the angle, is a function of time. So this derivative is not as simple as it might immediately seem, because it is the product of two functions of time. Therefore, I'll apply the product rule to it. X dot is equal to derivative of the first times the second plus the first times the derivative of the, back and forth like that. So it's equal to r dot cosine theta. Luckily, I have such brilliant students who can follow these arguments that I make. R theta dot sine theta. Let me give a little explanation there. The first term that I have here in the product rule is the derivative of the first with respect to time, which would naturally be r dot, the time rate of change of r, times the cosine of theta, leaving that alone. The next term is r, which is the first term there, times the derivative of the second. But here's the thing, theta is a function of time. So when I take the derivative of sine theta with respect to t, take the derivative of cosine theta with respect to t, I get negative sine theta, thus the appearance of the negative sign here. Negative sine theta multiplied by d theta dt, according to the chain rule of differentiation. And so that is x dot. Well, now I also need, what I ultimately need is x dot squared. So in order to get x dot squared, and things start to get a little bit complicated here, I'm going to have to square this thing. So bear with me while I do all this writing. This quantity, r dot cosine theta minus r theta dot sine theta squared, is going to be r dot squared cosine squared theta minus 2r dot theta dot cosine theta sine theta plus r squared theta dot squared sine squared theta. Yes, that's quite a bit. You might make an argument at this point, Shadley, I'm not terribly sure that this polar form was a good idea. Things are getting rapidly out of hand. Well, yes, things are rapidly getting out of hand, but they'll rapidly come in hand momentarily. So I just have to sometimes expand things in order to simplify them. So here I have this result, which is quite good. I needed x dot squared, and I have it. I have to make a similar argument for y dot squared. So here I go. Y is equal to, realizing that if x is equal to r cosine theta, then y is equal to r times the sine of theta. And that's not what I need. I need r dot. So pretty, fix that. I need y dot. That's what I'm looking for. So I'll have to take the derivative of that with respect to time. Well, you see the procedure is the same, because once again, I have a product of two functions of time. So I find I get a very symmetric result. It's going to be equal to r dot sine theta. Now, when I take the derivative of sine, it's just cosine. So it does not generate the negative sign it generated before. R dot sine theta plus r theta dot cosine theta. That is what the time rate of change of the y coordinate is. That is y dot. But I need y dot squared, so I'm going to compute y dot squared simply by squaring this whole mess, which gives me r dot squared sine squared theta plus a cross term, which is 2r dot theta dot sine theta cosine theta plus r squared theta dot squared cosine squared theta. And so through all this effort that I've put in, I now know x dot squared and y dot squared, and all I have to do to get v squared is to add these two together. Collective groan. Until you inspect it carefully and realize. Do you see that x dot squared has a term here, which is negative 2r dot theta dot cosine theta sine theta? And exactly the same term appears again below here in y dot squared, but positive. So when I add them together, the cross terms cancel. When I add them together, the cross terms cancel. So let me now write the sum for you. That v squared is equal to x dot squared plus y dot squared is equal to. Now I'm going to do some rearrangement of the terms here so you'll immediately see what's happening. There are two terms to this essentially. There's r dot squared cosine squared theta plus r dot squared sine squared theta. And adding to that a term that is r squared theta dot squared sine squared theta plus r squared theta dot squared cosine squared theta. Aren't I lucky? Notice in the first, I feel very blessed. Notice in the first term here that there's an r dot squared here that I could factor out, and I'm left with cosine squared plus sine squared, which is 1. Notice in the second term that I have r squared theta dot squared in both terms, which I can factor out, leaving me sine squared plus cosine squared, which is 1. And so I found, quite remarkably, quite delightfully, going lower than I've gone before, v squared is equal to r dot squared plus r squared theta dot squared. The square of the velocity in polar form, not Cartesian. The square of the velocity in polar form, not Cartesian, which, therefore, I'm happy to say that I can now begin to solve the problem. Here I go back to the total mechanical energy, which is 1/2 mv squared minus gmm over r. And so I'll write in 1/2 the mass times the quantity. And now I'm going to replace v squared with what I just found v squared to be equal to in polar form. R dot squared plus r squared theta dot squared. So that's my polar form of the kinetic energy for the thing in its orbit. Minus gmm over r. So there, minus gmm over r. And now that is the total mechanical energy. I have an observation to make about this total mechanical energy. It contains in it the quantity theta dot. You see the theta dot in the second term of the kinetic energy there, r squared theta dot squared. Theta dot is the time rate of change of the angle. And the time rate of change of the angle is the angular velocity, omega, right? Which means theta dot is related to the angular momentum of the orbit. One of Kepler's observations was that the areas swept out by the radius of the orbit are equal in equal times. The so-called law of areas, which we realized in a previous discussion was actually just the law of conservation of angular momentum. So I'm going to make an observation here. I'll put a little squiggle here. I'm trying to use the board as tightly as I can because I know I need a lot of real estate to make these arguments. So I'll make an argument here that the angular momentum is not an argument, it's a fact. The angular momentum is the moment of inertia times the angular velocity, I omega, something very familiar there. That the angular momentum is the moment of inertia times the angular velocity. Well, if I treat the planet as a point particle, I know what its moment of inertia is. Its moment of inertia is, in fact, mr squared. It's true, yes? Multiplied by the angular velocity, which is theta dot. Multiplied by the angular velocity, which is equal to theta dot. Going along further with my energy here, I'm going to distribute 1/2 m through these two terms here. So it's 1/2 m r dot squared, which for the moment I'm content to leave that term alone, plus mr squared, see the m goes through, theta dot squared, divided by 2 minus g, wrong m, minus g, again with the wrong m, it's just the order that I'm writing my m's in that's bothering me there, over r. Look how very similar the angular momentum looks to this term here. I have mr squared theta dot squared over 2, and here I have mr squared theta dot. I could express that second term in terms of the angular momentum. If I appreciate that mr squared theta dot squared divided by 2 is the angular momentum squared. You see, if I square the angular momentum, I get m squared r to the 4th theta dot squared. So squaring the angular momentum gets me the theta squared. But I've got to cut some stuff down. Squaring the angular momentum gives me m squared. I just want an m. So I'm going to divide by m. Squaring the angular momentum gives me r to the 4th. I just want r squared. So I'm going to need a little r squared in the denominator to knock that down. And my angular momentum squared lacks a factor of 2, so I'm going to throw a factor of 2 in there. Entirely in terms of the angular momentum and the radius, not the angle, which is going to become an important point in just a moment. So now the total mechanical energy of the thing, where am I going to write it? I guess I'm going to write it right here. My total mechanical energy has now become 3 terms, 1/2 m r dots, funny looking, familiar looking, plus replacing my inserting this new angular momentum type term that I have here, 2mr squared minus g mm over r. Notice what I have done, seemingly. I have eliminated the angular velocity from the equation. Seemingly. I have taken a polar equation in terms of radius and angle, and I have converted it into an equation that is purely radius. Do you see that the angle doesn't appear? And you say, well, yes, the angle, though, the rate of change of the angle, is inside the angular momentum. You see, it's just hiding in there. But that's okay because this angular momentum is a conserved quantity of the orbit. It's constant. It does not change as a function of time. And so I've written a radial form of the total mechanical energy. I've written a radial form of the total mechanical energy, and I'm going to give these two parts names. Look how this is like 1/2 mv squared. 1/2 m, certainly. R dot squared, where r is the radius of the orbit. As the planet goes around in its orbit, try to think of it only in the context of its radius. Ignore the angular motion now. Think of it only in terms of its radius. As it goes around in orbit, it comes closer and goes further away. Closer and further away as the orbit is elliptical. If I eliminate the elliptical motion, it makes its perihelion approach, closest approach, and then it recedes to the furthest recession, and it goes back and forth with a position vector that changes as a function of time. I call this term here, I'm not going to write it, I was thinking I was going to write it there for just a moment, I call this term here the radial kinetic energy. The radial kinetic energy. It's the kinetic energy associated with only the radial motion. Please don't mistake it for the total kinetic energy, it's not. The total kinetic energy is still 1/2 mv squared. But there's a kind of radial kinetic energy plus a potential energy that depends only on r. Remember, it's a characteristic of potential energies. Characteristic of potential energies is that they can depend on position only. It's one of the criterion for potential energies. They could rely on or depend on position only. And this is all constants of the motion with the exception of r. So I'm going to give this a name. I'm going to call this U effective. It is the effective potential energy. And it is a very, very useful way to be writing this expression because the effective potential energy might be very instructive to make a graph of this. So here I go, making a graph of the effective potential energy, U effective, as a function of the radius r. It's a little bit tricky, but this is what this graph looks like, and some of you may find it to be familiar. It looks like that. It starts out with a very, very high positive potential energy. And the reason why is that when r is very, very small, this first term in the effective potential energy, the one with the angular momentum in it, is very, very large indeed, and it fights off the 1/r term. And so the potential energy actually becomes positive. But as r gets larger and larger and larger, the 1/r begins to dominate. And so we drop down below here. Oh no, I think it'll be okay. And then drop down below here and go like that and asymptotically approach. This is what the radial potential energy looks like. When I'm looking at this graph, I should think only in the context of the radial energy. I learn so much from this graph. Recall that for potential energy functions like this one, the force is the negative of the derivative of the potential. There is a radial component of force that is the negative of the derivative of this potential. And so if I should happen to find the planet at this location, somewhere along the orbit, it would experience a force radially away. If I find it later on at some position further along here where the slope is the opposite, it would find a force radially towards the origin. And this is what causes the radial motion to go back and forth like this. But I'm getting ahead of myself. This is the effective potential energy. What I'm going to do is choose some total mechanical energies. The first total mechanical energy I'll choose is coincidentally down here, I'll call it E0. Total mechanical energy E0, which is coincidentally equal to the minimum of the effective potential energy function. Right there. If the total mechanical energy is equal to the effective potential energy, then the radius will not change. Think of this planet here as a marble sitting at the bottom. It's just going to sit there, stationary. Don't consider the angular motion. I'm talking about the radial motion. It'll sit there stationary at constant radius. This orbit, suggested by this lowest possible energy, is circular. This orbit suggested by the lowest possible energy is circular. Consider a higher energy. I guess I'll call it E1 here. This higher energy, we draw a line across, it represents that higher energy. Notice now that with the higher energy, there is now the possibility of having some radial kinetic energy. The radial kinetic energy associated with the radial motion of the planet. It can go to two extremes, and those two extremes are where the total mechanical energy intersects the effective potential energy here and here. And so what I would observe at this energy, E1, is that the planet will move back and forth between the two turning points, on this potential energy, a notion that we've talked about previously. But notice on the graph of this effective potential energy, it's not symmetric. It's not parabolic. It's not symmetric on either side. It sort of kicks out on the right-hand side of it. And therefore, the distance from this center, if you will, where the constant radius of the circular orbit was, that those two distances are in fact not equal to each other. I guess I'll draw that line up and sort of clarify that, draw a little dotted line in there, and see that those two radii are not equal to each other. No, they're not, because this orbit with an energy E1 is elliptical. That is an elliptical orbit. That is not proof, but it's a very strong suggestion that the motion that I'm describing here by observing the total mechanical energy of a planet in orbit around a star when a universal gravitational force is acting is very much like an ellipse. Other curious cases. Imagine that I give the thing, by the way, these two energies E1 and E0, do you see that they're below the axis here that I've chosen to be zero potential energy? They're below it. They're negative potential energies. When I had first derived the universal gravitational potential energy, I had suggested that gravitational potential energy is always negative for bound orbits. It's always negative for bound orbits. Look at these two turning points. The planet can't escape. That is, it can't get out to R further than this radius at aphelion right here. I suppose can I mark that on the graph? I'm going to give it a try. Radius at aphelion would be that radius right here. And over here would be the radius at perihelion. And it can't go further than those two radii. It is bound, trapped by its total mechanical energy. It's, as a classical physics concern, impossible for it to exceed those limits. Now consider an energy I call E2, just because I'm doing these in sequence here, that where the total mechanical energy of the orbit is equal to zero. Well, now I don't have to draw that line. That line is my R-axis here. Notice that with an energy equal to zero and the asymptotic behavior of U effective as R goes to infinity means that this thing can go on forever and ever. It is escape. It is escape. Remember when I demonstrated using Newton's universal gravitational law, the escape velocity assumption that I made was that an object would escape to infinity where the potential energy was equal to zero. What I'm effectively doing there is saying that the total mechanical energy is equal to zero, and that's escape. Orbits of this type are parabolic. You're getting the notion now that what's happening is that depending on how much energy the planet has in its orbit, I get different conic sections. And you might make a guess. It'd be fun for you to make a guess at this point. What will happen when I give it a positive energy here? I'll call it E3, a positive quantity of energy on the axis here. And imagine what the shape, well, I have a conic section left in my vocabulary of conic sections that I haven't used yet. Such orbits that have a positive energy are hyperbolic. Hyperbolic orbits with a positive energy. So with a little investigation of the effective potential energy, this radial term here, I'm able to show that I get all these different kinds of orbit, all these different behavior. That's a little bit different than proving. I still have a task that I want to derive an equation that says that the radius as a function of the angle theta is in fact an ellipse, or prove that it's so. There's a very good suggestion here, but there's no mathematics here, right? So I don't have, this is a suggestion, but not proof. So I want to prove that. Well, in order to prove it, what I need to do is I need to develop an expression that gives me a relationship between the differential of radius and the differential of angle. Because consider, please, that as the planet goes around and the angle changes and the radius changes, the rate at which the angle changes and the rate at which the radius changes, all of that changes continuously. So if I'm going to describe, and what I would like to do here is get you to appreciate the fact that this is what we're always doing in physics, is to write the differential of change and then integrate it. That is, what I seek right now is a relationship between d theta and dr, infinitesimal changes. And then in order to describe the entire orbit, I'll simply add up all the changes. Do you see that I'm using the same language that I was using in the introduction to the course, saying that I'm adding up tiny little bits of change, and that's what the calculus is all about. And indeed, that's the approach that Isaac Newton took. He realized that because the thing changed in every instant along the orbit, he needed a kind of mathematics that would appreciate that, and we simply add up all of the changes as you went along. It was very, very clever. So now what I have to do is to find a way to convert my expression for the total mechanical energy that I have here as a relationship between dr, the differential of radius, and d theta. Immediately you look at it and say, well, you've already given yourself a problem because you've converted the thing so it's entirely an equation of radius. So there's no angle in there. Yes, there's angle in there. It's hiding. There's angle is hiding in the motion. Not just hiding inside the angular momentum. In fact, I'm content to leave that angular dependence hidden inside the angular momentum as a constant of the motion. The constant of motion is a huge advantage to me from a physics point of view. I don't want to squander it by unpacking that. Let me make an observation here, because I'm starting right here with my sort of second phase of things. I have the description of ellipses there. I have the description of the energy. And now I'm going to observe the mechanics of the orbit here in this section of the board. R dot. which appears in the total mechanical energy right there, R dot, has a little bit of theta living inside of it. Let me show you why. With a little bit of elementary calculus that we all understand, R dot is equal to d theta. Oh, wow, it is not. I was being a little ambitious there with my language. My brain is a couple of pages ahead of what my voice is doing. So R dot is equal to dr dt. That's absolutely true, isn't it? And when I first encountered calculus, I was amused, delighted to find that I can chain rule as much as I want. So I'll write dr dt as dr d theta dt. That's totally legit. Chain rule. Haven't changed anything. But I have introduced a little bit of theta-ness to it. Dr d theta dt is dr d theta dot. Dr d theta dot. So there it is. Hidden inside R dot is theta dot. But look what I got. I got dr d theta. I got the relationship between the differential of radius and the differential of angle that I can then insert into my energy equation, and then I'm off to the races. No. Shidley, you've done a terrible thing here. Yes, you got dr d theta. That's lovely. But now you got theta dot jammed in there. Now you've got theta dot in your equation. You're not going to have an equation that you can integrate because you've thrown a theta dot in on... No, I haven't. Because theta dot is related to the angular momentum. And so I can immediately eliminate it from this expression. Watch. So is dr d theta dot, but... Put a little stage direction on here. But the angular momentum is equal to mr squared theta dot, which means that theta dot is equal to, just dividing this around, L divided by mr squared. Just the angular momentum divided by the moment of inertia. It's quite obvious. And so I can write now that R dot is equal to dr d theta multiplied by theta dot, but theta dot is L over mr squared. So now I have the relationship, dr d theta, that I want in terms of constants. L, the constant angular momentum of the orbit. M, the mass of the planet. And R, but it's okay to introduce R because I've got an equation that's a function of R. R is the thing that I'm going to be integrating. So it's going to work out fine. I'll get a little extra R into it. But in order to make the substitution, it's not R dot that I want, but in fact R dot squared, because you see here in my total mechanical energy, R dot squared appears. So I want to substitute that R dot squared in. So R dot squared is just simply going to be this thing squared. So I'm going to write dr d theta, in fact, squared, times L squared over m squared r to the fourth. Just like you, just like everyone, I get a little alarmed when the powers start exploding in the algebra that I'm doing, but it's okay. Turns out I have a little technique I'm going to use later on for reducing the powers, but still very much ahead of myself. So now what I'm going to do is write my total mechanical energy expression again, except I'm going to substitute R dot squared in. And in order to save myself some board space and repeating algebra over and over again, I wonder if you would mind. Here is my total mechanical energy equals 1/2 mr dot squared plus this quantity that I called the effective potential. Please don't mind if I subtract the effective potential to the other side to state that 1/2 mr dot squared is equal to the energy minus the effective potential. I'm going to do one big algebra step there because it suits me and it'll give me some utility of space here. So what I have is m over 2, which is 1/2 m, r dot squared. Well, I just realized that r dot squared is dr d theta, L squared over m squared r to the fourth, right there. That's what 1/2 mr dot squared becomes, is equal to the total mechanical energy E minus the effective potential. I'll be careful with these signs. It's now going to be minus L squared over 2mr squared plus Gmm over R. It's kind of amusing to me as I go along here. I've been just leaving that gravitational potential energy alone the whole time.
DRD.
Yes, thank you. I left off the square on my dr d theta. Happy. A cancellation. If you don't mind, a cancellation. Am I really going to cancel this? Are you really going to cancel it? I think I might. It's entirely possible. I'm going to cancel this m with this m down here and multiply through by the 2. If nothing else, find it reassuring that I really don't know what I'm doing here. I'm just making this up. But I'm making it up in a way, that I'm kind of cheating a little bit because I'm making it up in a way where I'm going to end up being right in the end anyways. So, why? Because I can trust the rational arguments that I've been trained to make quite meticulously, and with the support of folks watching for me making mistakes, it should turn out quite well. So I'm going to multiply everything on the left-hand or on the right-hand side through here by 2. So I have twice the energy minus the 2 in the denominator of L squared over 2mr squared will cancel as L squared over mr squared, which is kind of cute because it's just the angular momentum squared divided by the moment of inertia, plus 2g mm over r. That's what I have. Naturally, I'm now going to multiply through by the reciprocal of L squared over mr to the 4th, and this is really the dangerous part. This is the part where I'm apt to make algebraic mistakes, so please, if you would, follow along with the argument that dr d theta squared is equal to 2me over L squared r to the 4th. That's one term. Step back and make sure that I've done it properly. 2me r to the 4th over L squared. Notice that I wrote the r to the 4th off to the side. That's because I want to see the position dependent. I get all my constants together and then write the position dependence next to it, r to the 4th, just to keep things clear. Now, minus. I'm going to divide by L squared. I go to mr to the 4th. This is going to be r squared. Check me on that. By the way, I know I'm right, but I want to make sure that everyone in the audience is paying careful attention. And then this last term, which would be quite horrific indeed, plus, it's very, very strange, 2g little m squared, capital M, divided by L squared, and let's get the position dependence of it. It's r cubed. It's r cubed. Now, from a calculus point of view, I'm in great shape. From a calculus point of view, I'm in great shape because I have dr d theta, and I have entirely a function of r. I'm in great shape if I'm better at calculus than I actually am, because if I take the square root of both sides, solve for d theta, and try to integrate it, I can't integrate that. It's an integral that, so far as I know, doesn't really have a solution that I can work up, and maybe you'll be ambitious and try to integrate that thing. I have to do a little bit more to it before I can actually integrate it. I have to do a little bit more of a requirement here before I can integrate it. I'm going to make a substitution that will effectively reduce the powers, because I feel like if I can reduce the powers of the integration, that I might end up with an integral that's doable, if I can just get these powers down a little bit. So the way that I'll do the reduction of powers, and I'm going to write the assumption up here. It's kind of an awkward place to do it, but I'm using my real estate the best I can. I'm still going to need all of that space. I'm going to say let r be equal to 1 over u. It's kind of funny. I usually say let u be equal to 1 over r. Same thing. Let r be equal to 1 over u. That's an assumption that I'm going to make. I'm going to make a change of variable here that's going to improve my integral. And if r is equal to 1 over u, then the derivative of r with respect to u, quite naturally, is negative 1 over u squared. Negative 1 over u squared. And if I square that, then I guess I'm going to make a substitution. All right, that's right. dr squared is equal to 1 over u to the 4th du squared. 1 over r to the 4th du squared. I'm going to make that substitution here. And when I do, I'm going to do two things at once. I'm going to replace dr squared with 1 over u to the 4th du squared. And then I'm going to go along here on the right-hand side and replace all of my r's with u's. So this is what I get. 1 over u to the 4th power times du d theta. So I've transformed my integral. So change of coordinates of my integral, change of variable. Du d theta. Do you see I've replaced dr squared with 1 over u to the 4th du squared. So I'm fine there. On this side, 2me, and here I find myself writing these constants over and over and over again. It's a little frustrating. U to the 4th minus 1 over u squared plus 2g little m squared capital M over L squared 1 over u cubed. And so with a mind here to reducing the powers, I have this on the left-hand side, 1 over u to the 4th. I'm going to multiply through by that 1 over u to the 4th, so I'll rewrite here. Multiplying the left-hand side by 1 over u to the 4th is du d theta squared. Now on the right-hand side, I simply have to follow through multiplying each term by u to the 4th. The first term becomes 2me over L squared, because it's 1 over u to the 4th times u to the 4th, which vanishes, minus 1 over u squared multiplied by u to the 4th, which gives me u squared in the numerator, plus 2g m squared m over L squared times u. And I wonder if anybody immediately realizes what's happened here, and that it has become quadratic. Do You see here I have a term, I have three terms, one of which is u squared, another term that is u, and another term that has no u in it, that is u to the 0 is 1. And so it's actually a quadratic form. I'm going to take advantage of that and rearrange terms a little bit, because it's time for me to put this in a form that I can integrate. And so I want d theta on one side, and I want du on the other side of my expression. So what I'll do is I will take the square root of both sides, obviously, and invert it, so that d theta is equal to the square root. Now I'm rearranging terms here, so it looks sort of to be in the quadratic form. So the square root of negative u squared plus 2g m squared or m squared m over L squared u, which is the u term, plus the constant term 2me over L squared. All of that is under du. And so now I see I have a thing that I can integrate. If I can integrate the left-hand side, integral of d theta is in fact theta. And on the right-hand side, I'm performing an integral that's actually quite complicated. Nobody here, I think, knows immediately off the top of their head what that solution should be. But it's of a very pleasing form. What I'm going to do is write it down here as theta equals the integral of du divided by the square root of a quadratic. So I'll write au squared plus bu plus c. I immediately have a concern over here in my definition of the ellipse because of the way ellipses are defined traditionally in mathematics. I have a's, b's, and c's that appear over here. These are not the same. These are the constants in this quadratic, and I can do by inspection and see that a is equal to negative 1, that b is equal to 2g m squared m over L squared, and that c is 2me over L squared. So this is the integral that I need to solve. Now, certainly, I could take a pause here, take that integral aside, and find out what calculus techniques solve that particular integral. But it turns out that I think it's more convenient here that I'll simply look it up on an integral table. I happen to know the result of this integral. And so I'm going to move now over here where I'll start to flesh out what the actual result of this integral is, and therefore the shape of the orbit. So the integral of du over the square root of au squared plus bu plus c, it turns out, is equal to negative 1 over the square root of negative a, inverse sine of the quantity 2au plus b, divided by the square root of b squared minus 4ac. And naturally, there'd be a constant of integration associated with that, so I'll add a plus phi to the end of it. I know you're not accustomed to see me using constants of integration, but in this case, I haven't put limits on the integration, as I typically would, and so I'm leaving that constant there. And as you see, I'm going to be tricky with the constant anyway, so I appreciate leaving it there. I see a couple of simplifications immediately to this result. First of all, appreciate the fact that a is negative 1. And I just do that by inspection over here from my former equation. A is equal to negative 1, which is a convenience because here it's negative a in this radical here, which naturally just becomes 1. And so that whole term in front of the inverse sign just becomes 1. So I have negative the inverse sign of 2au. Well, a is negative 1, and u, remember my substitution, was that r is equal to 1 over u, and that means that u is equal to 1 over r. So this term in the numerator, 2au, becomes negative 2 over r. I'm not wild about leading negative signs, but I'll deal with that in just a moment. Plus b. Now b is this constant down here, 2g m squared m over L squared, which is a mouthful. I'm not going to insert that right now because we get very complicated looking in my equation. So I'll leave it as b for right now, particularly because in the denominator I have the square root of that same b squared plus 2, or plus, well, not plus, but minus 4ac. But a is negative 1, and so it's plus 4 times c. Well, again, by inspection, c is 2me over L squared. 4 times 2 is 8. So it's 8me over L squared appearing here in the denominator. Plus phi. Well, now I'm going to do sort of two steps at once. I'm going to realize that if theta is equal to the inverse sine of this quantity, then the sine of theta is in principle equal to that. Before I do that, I'll take my constant of integration here, which is a constant of integration associated with the angle theta. So it too is an angle, principle in radians, which I'll subtract to the other side, so it's theta minus phi. So what I'm looking at is the negative sine of theta minus phi is equal to, now I'm going to reverse the order of this numerator. Instead of being negative 2 over r plus b, I'll call it b minus 2 over r. Just simply find that more appealing. And in the denominator, where I have the square root of b squared plus 8me over L squared, I'm going to factor out b squared from that quantity. Notice what happens here in front. I've written a b times the square root of 1 plus 8me over b squared L squared. Now this quantity that appears in the denominator, the square root of 1 plus 8me b squared over L squared, I need to substitute in b there in order to find out what it's actually equal to. Well, b is quite complicated. It's 2g m squared m over L squared. If I make that substitution in for b squared, I find out that this term here is equal to 2el squared over g squared m cubed m squared. So the final denominator there, being multiplied by b, is the square root of 1 minus 2el squared g squared m cubed m squared, which I'm going to call lowercase e the eccentricity. Refer back here to the ellipse as I defined it. Here I have the eccentricity is equal to the square root of 1 minus b squared over a squared, and I'm going to call this quantity here the eccentricity. And so the eccentricity is that. It greatly simplifies my algebra here because now I have b minus 2 over rb times e, the eccentricity. Now on the left-hand side, I've left behind here negative sine theta minus phi. Well, this is where this constant of integration, phi, comes in handy. Because I'm looking for a relationship ultimately that has a cosine in it and not a sine. And this phi here gives me the perfect opportunity to change the sine into a cosine. I simply have to choose phi appropriately is the right amount of phase to shift the sine wave over until it becomes a cosine. In fact, I could choose it in such a way that the sine of theta minus phi is actually equal to negative cosine, so the negative sign disappears. I'll multiply the eccentricity from the right-hand side over to the left, so that e cosine theta is equal to b minus 2 over rb. And so I have an expression here where it's time to start fleshing things out by adding in more of what these values are equal to, particularly the value of b. So I'll divide, because it's all over b, I'll divide both by b. Well, b divided by b is 1 minus 2 over r multiplied by the reciprocal of b. So L squared over 2g m squared m. And notice the 2's immediately cancel. So I'm left with a multiplying factor L squared over g m squared m there, which I'm going to call lowercase l. And of course, by naming that lowercase l, I'm referring over here to what I had called the semi-latus rectum and said that I would use lowercase l for that quantity. So now I have the eccentricity times the cosine of theta is ultimately equal to 1 minus L over r. Now I need only solve for r because everything's in terms of constants. So I'll subtract 1 to the other side of the equation, which gives me negative 1 plus e cosine theta is equal to negative L over r. Solve for r. Ultimately, r as a function of theta, which is my ultimate goal, is equal to L over 1 minus e cosine theta, which I'd established at the beginning of the lecture is in fact the equation of an ellipse. So it's sort of summary of what's happened here is I wrote the energy, total mechanical energy, and by introducing the differential relationship between differential change in r dr and d theta, I'm able to create an expression that I can integrate, and then after I make that integration, I can manipulate it into r as a function of theta. And I discovered, just as Isaac Newton did so many years ago, that the motion of the planets around the sun are in fact ellipses.